All right, welcome everyone to today's video here. We're going to talk about constant volume calorimetry, talk about calculating heat under constant volume conditions, right? And so where we begin is from our first law of thermodynamics, right? That change in internal energy is related to some amount of heat and work that's been done and transferred, right? If we write this, okay, in terms of some small infinitesimal change in internal energy, right, that's related to some small infinitesimal change in heat, some small infinitesimal change in work, right? And here I've broken my work equation, okay, into two things, right? I got our expansion work that we've been talking about, and then extra work, okay? Right, extra work is electrical work, other types of forms of work that can be done, and we're just going to ignore those, right? Set that equal to 0, right? We're not going to bother with that stuff and just talk about expansion work and heat, okay? So it's considered a constant volume process, right? Where, again, we're assuming there's no extra work, okay? Well, that expansion work, right, is just related with minus P external dV, right? Derived to that before, okay? Well, if there's no change in volume, right, constant volume, that means dV is equal to 0, so dW is equal to 0, right? So under these conditions, right, du is just equal to dq under constant volume conditions, right? So this result, right, is general for constant volume processes, okay? So under, right, constant volume, this is very general, okay? If you integrate that out, right, that means the total change in internal energy is just related to the total heat that's been transferred during that change in state, okay? And so, right, and that's only under constant volume conditions, right, that this delta U is equal to Q under constant volume conditions, right, because there's no expansion compression work. And in this class, we're typically ignoring and assuming there's no extra type of work as well. Okay. So, right, this change in internal energy related to Q, right, it is something that is often measured and carried out in a constant volume calorimeter, okay? Right? And how these things work, right, is, for example, an adiabatic balm calorimeter is a constant volume calorimeter, right? In this adiabatic balm calorimeter, right, you have, okay, your system, which is some chemical reaction you care about, okay? That reaction takes place in some constant volume container. That container is connected to a heat bath, a bunch of water on the outside, okay? Right? That water on the outside has a thermometer in it measuring the temperature, and then the wall to that water to the outside world is adiabatic. Okay? You have an adiabatic wall between the water and the outside world, okay? And it's in a closed container, so that means no heat is being transferred to the outside world and no matter is being transferred to the outside world, right? So I have an isolated system, right? And so in this balm calorimeter, right, my system is the inside, it's called the balm, right? This chemical reaction, this typical combustion reaction that takes place, okay? My surroundings are the water, right, is that water bath, okay? And we assume there's no heat loss, anything else, right? Whatever heat is generated by the chemical reaction is absorbed by the water and goes nowhere else, okay? And so again, this is an isolated system, right? So that is my system and surroundings, right? Chemical reaction and the water bath, okay? And nothing else matters, right? Nothing else is in contact, either thermally or otherwise, with my system and surroundings in this case, okay? Right? And so often what we will do is in that surroundings, right, we will use that thermometer to measure the temperature change of that water, okay? That temperature change of the water in the surroundings, right, is going to be negative the temperature change in my system, right? Because if heat is transferred from my system to the surroundings, okay, right? That means, right, that Q is less than 0, right? But Q of the surroundings, right, is greater than 0 because it absorbed heat. Right? The surroundings absorbed the heat. It got energy, right? So, right, the surroundings heat and the system heat are always opposite side, right? That Q is equal to minus Q surroundings, right? It's in general true, right? So the constant volume heat that was transferred to the surroundings is just negative of the original, right? And then the heat, right? Calculating the heat in the surroundings is related with the heat capacity times the change in temperature of the surroundings, or in this case, of that water. Okay. And some of this should be making some sense, right? If you recall back in general chemistry, talk a little bit about heat capacities, right? I'm sure you did a kind of a calorimetry study using styrofoam cups or something of that nature, right? A very common lab to do in general chemistry. Okay. And that C, right, is this heat capacity, okay? It's something that's standardized, right? You have to determine what the heat capacity is of your calorimeter by using a known experiment, a known transfer of heat to determine that, okay? And it can also be referred to as the calorimeter constant. I'll often refer to it as just the heat capacity, but just note that you might see it in a problem somewhere called the calorimeter constant. Okay. What is the heat capacity? What is that defined as, right? Well, the heat capacity is the amount of energy required to raise the temperature of a substance by 1 degree Kelvin, okay? Or you can think of it as 1 degree Celsius, right? Because a degree Kelvin change is the same thing as a degree Celsius change, right? And that's in general the heat capacity. Often we'll talk about the molar heat capacity, okay? See some N, right, to the molar heat capacity, which is just the heat capacity divided by the number of moles, right? Or the specific heat capacity, it's often symboled CS, okay? That is the heat capacity divided by the mass, okay? Right, the heat capacity itself has units of joules per Kelvin, right? Because it's the amount of energy in joules that's required to raise the temperature by 1 Kelvin, okay? While the molar heat capacity, right, is then joules per Kelvin mole, and specific heat capacity is joules per Kelvin gram, right? Or kilogram, depending. Okay. And often, especially when we talk about gases, we'll talk about the constant volume heat capacity of a gas and the constant pressure heat capacity of a gas, right? Often these things are also given in per mole quantities, okay? So we might have CV, M, right? It's not N, sorry. M is what it's used, right? CVM, CPM, right? Are the molar versions of the constant volume heat capacity and constant pressure heat capacity. Okay. Right, mathematically, that heat capacity, right, you can think of the heat capacity as sort of a change in energy over a change in temperature, right, which is just the slope of a line, right, du dt, okay, right? So the constant volume heat capacity is just related with du dt, right? What's that internal energy change with respect to temperature at some given temperature, okay? That slope, the derivative, okay? Right, we can write this in general, right? Using our multivariable kind of calculus stuff, right? You can write that heat capacity CV as del U del T at constant volume, right? Because that's where heat capacity is defined as, right? It's at a constant volume process, right? So CV specifically, right, is defined at constant volume, right? CP would have a similar thing, right? CP would be del U del T, constant P, okay, right? Right, so the heat capacity at constant volume, right, is holding volume constant, right? And it's looking at the change in energy with respect to change in temperature, okay? Right. Actually, this isn't del U, this ends up being dH dt, but we'll get to that later, right? Okay. But this, right, this is partial derivative, right? Again, we treat this as just du dt, right? Assuming everything else is constant, right? And that's what the heat capacity at constant volume is equal to, okay? Is that slope, that derivative of the internal energy with respect to temperature. right? Just again, recall that we treat these partial derivatives just like regular derivatives. We're treating, holding everything else constant, okay? Right, we went over that in the math review, but just as a reminder, right, that don't worry about what these partial derivatives, right, the symbols used and stuff, just think of it as like d dx, right, where everything but x is constant. Okay. So some properties of the heat capacity, right, is it typically is temperature dependent. Often we'll just assume a temperature independent form, but it can be temperature dependent, especially at very low temperatures. And C is an extensive property, right? So the heat capacity itself depends on the amount of stuff you have, right? The more stuff you have, the more energy it takes to increase its temperature, right? You try to boil a very small amount of water versus a very large amount of water, right? It takes more energy to boil a large amount of water, so it makes sense, right? Now things like the molar heat capacity is intensive, right? Because I've taken an extensive quantity and divided by the total amount of stuff, right? Divided by the number of moles. So molar heat capacity is intensive, but in general, the heat capacity itself is an extensive property. Okay. Right. And again, right, that heat capacity is right, defined mathematically as this partial derivative of the internal energy with respect to temperature holding volume constant. Okay. So, right, using that relationship, we can show at constant volume, right, that du dt cv, right, just multiply dt on the other side, you have du equals cv dt, okay, right. If cv is constant with temperature, which we'll often assume, right, this relationship then is true, that delta u is equal to cv delta t, okay, right. And that result, while we've derived this change in internal energy, right, that delta u equals cv dt, or delta t, sorry, right, we've derived this assuming a constant volume process, right? Remember, u, internal energy, is a state function. So if I get from point A to point B, right, and I do that change in state, whether it's constant volume, constant pressure, constant temperature, whatever, right, the change in internal energy, I can calculate it always using cv delta t, okay, assuming heat capacity is constant, right? If the heat capacity changes, then that formula is slightly different, right? Right, this equation up top, right, du equals cv dt is in general true for any type of change in state, right? This one here, right, is specifically true, right, if cv is constant, right? So at a constant cv, delta u is equal to cv delta t, okay? And that change in state, right, that formula to calculate the change in internal energy does not depend on how I made that change, okay? Even though we derived it in a specific way for a specific change, that formula does not depend on how I've made that change in the end, okay? That no matter how I go from point A to point B, I can always calculate delta u as just cv delta t, okay? Because it is a state function. It's path independent, right? So it doesn't matter, okay? Right. Now, a little bit later, we'll talk, right, in the semester about how this change in internal energy is not just cv dt, right, but also has some volume dependence, right, related with this pi sub t, okay, which is the internal pressure of a gas is what it's defined as, right? Pi sub t is defined as the internal pressure, okay? For an ideal gas, pi sub t equals 0. So for an ideal gas, du does equal cv dt, okay? But for real gases, pi sub t is non-zero, though it's typically very small, okay? And so often we can use this simple du equals cv dt for any problem in general, right, unless specifically specified otherwise that we need to include this kind of internal pressure term, okay? Which again, if cv is constant, right, then we can simplify this to just delta u equals cv delta t, right? And that works for any problem, okay? Because u is a state function. And we'll see lots of examples of this in class and talk more about this fact that it's a state function and yada, yada, yada. But yeah, it's a very useful thing to have state functions because then we just need to worry about one way to kind of compute something because it's path independent, so it doesn't really matter how I did it. The change in that value will always be related to this equation. Okay. All right, and that does it for talking about heat capacity constant volume, and what change in U is in Q at constant volume conditions.